Hello everyone, welcome to our discussion of properties of limits. As you recall, in the last video we introduced the concept of limit and how the independent variable x approaches to some value, and we had some value for the function as x approaches some other value. So in this case, in today's lecture, we will talk about properties of limits in general. So let's begin with this assumption that suppose that C, capital C, is some constant and the following two limits exist. In other words, when we say these two limits exist, by that we mean that as x approaches from to a from left and right, those two values are equal. Therefore, we can say the limit of the function f of x as x approaches a does exist. And we're going to assume the same thing for function g of x, that it does have a limit as x approaches a from left and right. If that's the case, then we can say the following properties for the limit of these two functions. So the first one, we can say that the limit of the sum of the two functions f and g as x approaches a is equal to the sum of the individual limits. The same thing for the function g of x. So a lot of these properties, if not all of them, are pretty obvious, yet we still want to mention them so it's in our mind as we simplify the upcoming examples. Okay, so that's the first one. And then we have another property which talks about the difference between the same two functions as we take the limit of the difference. So we can say that the limit of the difference of those two functions as we subtract them from one another is equal to the difference between the individual limits of those functions. Okay, pretty obvious, right? Pretty intuitively obvious. And we like that because it's easier to remember them that way. Okay, so we said that C was a constant. Now we're going to use it. So the limit of C, or that constant, times a function as x approaches a would be equal to C times the limit of the function. In other words, C can be factored out and placed in front. Like that. Okay? Very easy to remember all of these properties. So the next one, so we've talked about the addition, subtraction, multiplying the function, the limit of a function by a constant, and now we talk about the limit of the product of two functions. So as you can guess, that is equal to the product of the individual limits of those functions. Limit of g of x as x approaches some value a. So the first part we're going to introduce all these properties, and in the second And after this, we're going to use them. And I'm sure you can guess the next one has to do with the limit of the two functions divided by each other. F of x divided by g of x would be equal to the limit of those functions divided by each other. Like that. And also the same thing for the function in the denominator. Like that. Okay, and of course, let me add quickly that for this one, we want to say if this is the case, if the limit of the function that's in the denominator as x approaches a is not equal to 0, right? We don't want the limit to equal to 0. In other words, if the limit of g of function g of x exists, but it's equal to 0, then this does not apply to that. Okay, for obvious reason, we don't want the denominator to be 0. We can say that limit of a function to some exponent, let's say n, as x approaches some value a, is equal to the limit of that function raised to this power. In other words, so we can put the limit on the inside. Limit of the function as x approaches a raised to n. And let's also describe this n, that n is any positive integer. So n positive integer. Okay, like that. Here we have a few more rather obvious properties of limits. We can say that the limit of a constant, so there's no variable involved, right? Just the limit of a constant, as x approaches to some value, what do you think this should equal to? It would equal to c itself, right? The constant, because there's no variable involved. And then, of course, this property, limit of x as x approaches a, of course, what do you think about that? What would that equal to? It would equal a, right? As x approaches a, the limit of that function is equal to a. And the limit of a power function that is equal to that, of course, when x approaches a, right? This would be equal to that. Once again, we want to describe n, which is any positive integer. And of course, we can't come this far and not talk about the root function, right? So let's also talk about that. So the limit of a root function with index n as x approaches a. I'm sure you can guess what this result will look like, right? It would be n through to of a, right? Of course, this would again be where n is a positive integer. integer, like that. So this was just a variable, and now we can say this. We can say something similar, but a little bit different, when we have a function here. So inside the radical, I mean, if the limit of nth root of function f of x as x approaches a, it would equal to nth root of limit of that function on the inside. Limit of the function as x approaches a. So where n is a positive integer, and of course we assume that this limit is greater than 0, assuming that limit of f of x as x approaches a is greater than or equal to 0. Okay, so it can't be negative. And we knew that from basic algebra classes. Okay, so let's talk about a property that is called the direct substitution property. So suppose we have f that is a polynomial or a rational function, either one. And suppose that a, the constant a, is in the domain of f. Of course, a, as you know, is always in the domain of f if f is a polynomial. So by this and, we are talking about when we have a rational function, then this and, if a is in the domain of f, then we can say that the limit of function f of x as x approaches a is simply equal to f, that function evaluated at a. This is the property that your book talks about. But in practice, I better add something here, which is not part of what the property is. So the property, I should maybe box it like this. So this is the actual property, as mentioned in your book. But there is a piece of this that's very important to remember, extremely important, as you actually apply this to limit of functions. Then let me add this, a very important note. So important note is that always simplify f of x to the extent possible before calculating the limit, right? Before doing this, before substituting A in this direct substitution property. So we want to do what this property is saying, which is substitute the A for x in function f of x in order to find its limit at that value. But we want to do that after, or always simplify f of x, or simplify this before substituting A for x. Okay, very, very important to remember that. Because a lot of times when you have, especially when you have rational functions, when you directly, immediately, even though there is a limit for the rational function, when you directly substitute this A for x, you're going to get an undefined function. But not so after you simplify the f of x to the extent possible. And then, so you want to always simplify this function to the extent possible before substituting this limiting value in the function for x. Okay, very important to remember. Okay. And of course, the same goes for when you have trigonometric functions, right? So this f of x can be either the polynomial rational functions, or when you have trigonometric functions. So or when you have trigonometric functions, and this is what we mean. So suppose if you have limit of the sine of theta, theta being some angle, as theta approaches A, and this would equal to sine of A. I mean, not sine of theta, but sine of A. And the same thing that I said in this red ink goes for this too. So there are cases where you want to simplify the trigonometric function before you apply this property. And so limit of cosine of theta as theta approaches A would be equal to cosine of A. So here is a useful theorem, and this will lead to the next one, which is the squeeze theorem, but let's start with this one. I'm sure you can see a lot of these properties, if not all of them, are very, very intuitively obvious. So it makes it much, much easier to remember them. So if we have a function that is less than or equal to another function, when x is near some constant a, and the limits of f and g exist as x approaches A, of course the implication here, as you remember from the last video, that when we say that the limit exists as x approaches A, that we mean x approaches A from both sides, right? So the limit should be equal. X approaching A from both sides should be equal. So if that's true, then we can say that the limit of the left side is also less than or equal to the limit of the right side as x approaches A. In other words, the inequality holds not only for the original functions, but also for the limit of those functions as x approaches A. Okay, and I should actually box this as well. Like that. Now the next one for the squeeze theorem, very, very important again, and not only for this class or the higher calculus classes, but also for those of you who are math majors. You will use this theorem a great deal. Sometimes it's called the pinching theorem. The squeeze, and let me just put in quotes, also the pinching theorem, aka so if we have three functions such that f of x is less than or equal to g of x, such that g of x is less than or equal to h of x, if we have this scenario with three functions, where x is near A and limit of the function as x approaches A is equal to limit of h of x as x approaches A equals L. Okay, then so basically what this is saying is that if you have three functions such that the limit of the end functions, f of x and h of x, is equal and approaches some value L, then the limit of the middle function, the one that's in between those two, as x approaches A, must also approach L. And that makes sense, right? Intuitively obvious statement. So then the limit of the middle function g of x as x approaches A must also be equal to L. Okay, very important. This one is even more important than the property above or the theorem above it. Let me box that like that. Okay. Okay, so we've shown some properties. Now let's go over some examples, which is basically application of these properties to these functions that we have. So let's start easy. It's always a good idea. With this example, we want to know that given three functions, let's call them f of x equals 4 as let me say the limit of this function as x approaches 2, if that's the case, and limit of function g of x is equal to -2 as x approaches 2, and limit of h of x is equal to 0 as x approaches 2. Okay, so these three functions that each have a limit at 2 equal to these values, 4, -2, and 0. Then we want to know, or we want to find the limit if it exists, right? It may not exist, but if it exists for this limit of 3 times f of x divided by function g of x as x goes to or approaches 2. Okay. So of course, from the properties that we just talked about, we know how this will translate using those properties, right? So we will have limit of, so we have 3 times limit of f of x as x approaches 2 divided by limit of g of x, function g of x as x approaches 2, right? This is, we know this from the properties that we just introduced. So now 3 is a constant by itself times limit of f of x as x approaches 2, right? So that was, we are given that value, it's 4. So 3 times 4 divided by limit of g of x as x approaches 2, it is -2, right? So -2, we have 12 divided by -2, which is -6. Okay. So let me, so this was just one example using these. The rest of them are very similar. So there was no part B to this, but we have plenty of examples coming up. So this one is a bit of a graphical one, that it's the kind that we saw in the last video, which is good. So it'll remind us of these kinds of problems as well. So we want to know, given the following graphs, we want to evaluate each limit. And of course, if the limit exists, right? Which means if we evaluate the limit from both left and right, we must get the same value, right? From both left and right. That's how we know that the limit exists. And let me grab my ruler here because I want to draw those lines nicely. So, all right, so we have, let's draw them. There are two graphs here. I'm going to draw them side by side. Move this up a little bit. So we have one here and another one here. That. F of x, and of course This is f of x. Okay. All right, so we have then 1 and 2 along the x-axis, also -1 and -2 on this side, and -1 on the y-axis here, and of course 1 and 2 along the positive y-axis. And the graph that we are given is looks like this. So we have a point here such that the graph comes and connects to it like so, and then we have a point here at 2, 2 right here. We have a hollow circle, and then we have these 2 points connect each other right through the center or origin, like that. And then we have another extension on this side. Okay, so that's one of the graphs. And then we have on this side, so we have 1 and 2. And we have 1 and 2. And right at where we have 1, 1, we have a filled in point here. And then at 1, 2 right here, we have a hollow circle like that. And then here along the, we have -1. And then we have -1 and -2. -2, like that. Okay, so we have a line that comes from, and we have also a point here at -1 and -2, some point here. And so we have like that. That's part of the graph. And then we have also, we have this line extending from like that, curving and going through 2, 0 at this point. Okay, and I should correct myself here. This one is f of x. F of x, and this one though is not f of x, this is g of x. Okay, so 2 different functions there. Okay, so given these graphs, then we are asked to evaluate each of these functions. Let me write them underneath. So we want to evaluate the limit of this, the summation of 2 functions as x approaches 2. And here we want to evaluate the limit of square root of 3 plus f of x as x approaches 1. Okay. All right, so using the properties that we just introduced, we know that this would be equal to the summation of the individual limits, right? So limit of f of x as x approaches 2 plus the limit of function g of x as x approaches 2. Now, the function f of x as x approaches 2, that means from both sides, right, from the left and from the right, is equal to 2, right? We can read it from the graph. So this one is equal to 2 plus I'm going to try to keep everything on the screen as we go. I think this should do it. And limit of function g of x, which is this one, as x approaches 2 from both sides, it certainly has a limit, right? What is that? What do you read from the graph? The limit of this function g of x as we approach 2 from both sides is 0, right? Plus 0, so 2 plus 0, which would be equal to 2. Okay, so we have that. And then also for this one, we have the limit of, so using the properties that we have, what we can do is say square root of, we can put the limit on the inside, right? So we can say the limit of 3 as x approaches 1 plus the limit of f of x as x approaches 1, right? So now we know again from the properties that this value is just equal to the constant, right? So we have square root of 3 plus limit of function f of x as x approaches 1. Let's see. So x as x approaches 1 from both sides, we have that. So it points to the value of the function being 1, right? As x for function f of x, as x approaches 1 from both sides, the value of the function approaches 1. We can read it from the graph. So that would be 1. So then we have square root of 4 or 2 again. Here. Okay, like that. Okay, so I hope this is starting to make sense. The properties are very intuitive and obvious. All right, so let's go over more examples. In this series of examples, we want to evaluate each limit, of course, if it exists. So we have the limit as x approaches -1, 2x squared plus 3x plus 1 divided by x squared minus 2x minus 3, and we want to know what this is, what this equals to. Now, it's here where I mention that even though this property of the direct substitution property makes a great deal of sense, we need to remember this portion that I wrote in red ink, that we always want to simplify f of x to the extent possible before substituting a for x in order to find the limit. Okay? If you don't simplify the expression here, what do you get? If you just substitute -1 in this rational function without simplifying this rational function, what you end up with is -1 squared, which is 1, positive 1, minus 2 times -1, which is positive 2. 2 plus positive 1 is 3. 3 minus 3 is 0. So you end up with a denominator that is 0. But we want to simplify this expression, right? So let's do that. And we've learned how to do this in basic algebra classes. So we have, this is a quadratic equation. We can factor this, right? It's an easy one to factor. So we can say 2x plus 1 times 2x times x is going to give us x squared. How do we get 3x? Well, how do we get 1? 1 times 1. Everything is positive, so plus 1. And then the middle term, 3x, can be obtained by 2x times 1 plus 1 times x. So that's the factorization of the numerator, expression in the numerator. And this one also easy to factor. So we have x minus 3 times x plus 1, right? X times x is x squared. X times 1 is positive x. Minus 3x is minus 2x. Minus 3 times 1 is minus 3. So we got it. Now let's simplify. So we have x plus 1 and x plus 1 that cancel each other out. We end up with 2x plus 1 divided by x minus 3, which is the simplified version of that rational function. Now let's apply the same limit to the simplified version that we just found. So we have the limit of 2x plus 1 divided by x minus 3 as x approaches minus 1 is equal to, let's simply, we're gonna now, after we simplify, we're gonna carry out with this direct substitution property. In other words, we're going to replace x in the rational function or in the simplified version of it with a. Okay, we're going to do that now. So 2 times minus 1 plus 1 divided by minus 1 minus 3. So we have minus 2 plus 1 divided by minus 4. And we have minus, let's see, so we have minus 1. And so we have minus 2 plus 1. So that'll be minus 1 divided by minus 4, or 1 over 4. Okay, like that. Okay. So another example. Suppose we want to calculate the limit of square root of 4u plus 1 minus 3 divided by u minus 2 as u approaches 2. Okay, we want to calculate that. So here, we need to, if you replace u with 2, you can see right away that it won't work, right? The expression is undefined, therefore it looks as if the limit does not exist. But let's see if we can somehow simplify this expression by first rationalizing the numerator. Okay, let's do that. Let's see if that is going to help us. So we're going to have square root of 4u plus 1 minus 3 over u minus 2 multiplied by square root of 4u plus 1 plus 3 divided by square root of 4u plus 1 plus 3. Okay, So in the numerator, it's clear what we're going to have, right? We're going to have the 4u plus 1 and then minus 9, right? Like that. From the special product formula that we have, right? Using, I'm sure you remember this, but just in case, using x minus y times x plus y is equal to x squared minus y squared. That's what we use in the numerator here. And then in the denominator, we're going to have u minus 2 times all of that, which is square root of 4u plus 1 plus 3 close parenthesis. Okay, so in the numerator, what we have is, I'll try to fit all of this in the space that I have left. So 4u minus 8, of course, minus 9 plus 1, and then over all of this in factored form. So it's to our advantage if we keep things in factored form. So 4u plus 1 and then of course we can factor the numerator. So 4 times u minus 2 divided by u minus 2 times square root of 4u. I have not forgotten about the limit, but for now we're just simplifying. 4u plus 1 plus 3, right? Of course, you can see that these two cancel out. And now we can take the limit of this simplified rational function. So we have the limit of 4 divided by square root of 4u plus 1 plus 3 as u approaches 2. Right? So, and of course, now after rationalizing the numerator, if you substitute for u with 2 to apply the property that we have, right, to apply the direct substitution property after we simplify the expression, we're not going to get a 0 in the denominator, which is what we want. Okay, so this will be equal to 4 divided by square root of 4 times 2 plus 1 plus 3, of course. Okay, so that would be 4 divided by 3 plus 3, 4 divided by 6, and of course that is 2 divided by 3. Okay, all of that. So with simplifying that rational expression, we were able to find the limit. Okay, so that's as best as I can get it with everything on the screen. And like that. Okay. So next example. Before we take a look at the next example, I want to remind you of some of the special product formulas that we had, or special formulas that we had from the past. These are important to remember. So recall these from the past, basically. So we have x cubed plus y cubed, that is equal to x plus y times x squared minus xy plus y squared. Remember that? And then also remember the difference one. So this was the summation, and also we have x cubed minus y cubed, that is equal to x minus y times x squared plus xy plus y squared. Remember that? And of course we have the other two, which are as follows. So x plus y cubed is equal to x cubed plus 3 times x squared y plus 3 times xy squared plus, of course, y cubed. Okay, and we had the x minus y cubed version of that. We have x cubed, and then we have plus or minus 3x squared y plus 3xy squared minus, of course, y cubed. Okay, just remember or recall these properties from the past. Okay. So now we can talk about example C, which is asking us to find the limit of this function, this rational function. You can see right away the connection, right? Now we can use that divided by h as h approaches 0. Well, it's clear that if we substitute for h with 0 right away without simplifying, the limit is not going to exist because this whole function is going to be undefined. So let's see if we can simplify this before we substitute for h with 0. So to do that, we're going to make use of this property, this one, this expansion of x plus y, or this shortcut formula, right? These are basically shortcut formulas. So we have x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed. All of that, that's this x cubed, right? Minus x cubed divided by h. Okay, for now let's simplify, and then once we're done, we're going to apply the limit to it. So we can see right away that this x cubed and this x cubed cancel each other out, and we end up with, let's see, do we end up with, yes, so these terms. So we have 3x squared h plus 3x h squared and plus h cubed, all of that divided by h. Okay, so now we have, let's see, what do we have? What can we factor from here? We can factor the h, of course, from all of these. This one has h squared, and h cubed. So we have h factored out, 3x squared plus 3xh plus h squared divided by h. And so that h, those two h's cancel out. So now let's apply the limit to what we have left. So in other words, we have the limit of this function, whatever is left, 3x squared plus 3xh plus h squared as h goes to 0. Okay, so replacing there, we have 3x squared. Sorry, let me correct that with my thick marker here. So this one will simply be 3x squared. It'll stay as that. There's no h here, so, and then we end up with plus 3x times 0 plus 0 squared. Of course, these two terms drop out, and we end up with just 3x squared, like that. Okay? So this example, again, highlights the importance of whenever you have a direct substitution of limit for a fraction and it doesn't work out in the beginning, then you need to simplify. Sometimes it might work right from the start, in which case you don't need to simplify, or you just simply substitute for that variable and then simplify the final answer if there's a need for that. Okay, so having talked about this, then there is a trigonometric property that is very, very important and very easy to remember, actually. Very simple but very important trigonometric or property, or the limit of a trigonometric function, which says, so here's an important identity. Where it says that if you have sine of some angle divided by that angle, and if you take the limit of that ratio as the angle approaches 0, then this is always equal to 1. Right? Very, very important identity. We have a lot of use for this in this course, and if you're taking higher level calculus classes, you will see this again and again. Okay. Okay, so we've switched to trigonometric based examples, so let's continue with that. So in this case, we want to use the squeeze theorem. Again, one of the important theorems we have in this course. To show that the limit of x squared times cosine of 20 pi x as x approaches 0. We want to show that the limit of this expression as x approaches 0 is equal to 0. Using the squeeze theorem, of course. Okay. Otherwise, we could just say, oh, just replace x with 0 and you're going to get 0. But we're not going to use this theorem, the direct substitution theorem that we talked about before, right? This one. I'm trying to find it right now. Can I find it? Yes. So we could show that the left is equal to 0 by using this direct substitution property, but that's not what we're asked to use. We're asked to use the squeeze theorem, which we talked about here on page 3, which is this one, right? What did squeeze theorem say? It said that if you have 3 functions and the limit of the functions that are on each end of this inequality, if they have a limit equal to some value for both of them, then the limit of the middle function as x goes to that same value is going to also be L, equal to the limit of the functions on either end. So if these two end functions approach some value as x approaches to a, then the middle function also must approach L, or that same value as x approaches a. Okay? All right, so we need to use that theorem. Okay, first of all, we know that the cosine, this piece, cosine of 20 pi x, remember from trigonometry that this has a range, right? So it varies from -1 to -1, right? So this piece only, so solution, this piece only varies from, so let's write it down, cosine of 20 pi x varies from -1 between -1 and 1. Okay, we know that from trigonometry. Now, let's multiply all sides of this by x squared. Okay, so multiply all sides by x squared. So x squared times this, what do we get? We get minus x squared, right? Then x squared times all of that, we get x squared cosine of 20 pi x less than or equal to x squared times the far right side, and we get that. Notice now, after we did that, we ended up with that full expression, right? So we began with remembering that this piece varies from -1 to 1. Somehow we had to make the connection between what we have, this expression, and the squeeze theorem, right? This is how we were able to do it, by remembering that this quantity ranges from -1 to 1. Then we multiplied all sides by x squared. Now we have that whole expression in a situation where we can apply the squeeze theorem, right? So now let's take a limit of x as x, or limit of all sides, not x, limit of all sides as x approaches 0. So let's do that. So we multiply all sides by x squared. We did that. Take the limit of all sides. Take the limit as x approaches 0 of all sides. Okay, we're going to do that next. And so we have the limit of minus x squared as x approaches 0 less than or equal to the limit of that whole thing, x squared cosine of 20 pi x as x approaches 0, and of course less than or equal to the limit of x squared as x approaches 0. Okay? Now, what do we get on this side? Of course, we get 0. What do we get here? We have the, let's keep this, limit of the, because we need to apply the squeeze theorem, cosine of 20 pi x as x approaches 0. And of course, on the far right side, we get 0 as well. So by squeeze theorem, notice that the limit of both ends as x approaches 0 goes to 0. So therefore, the limit of the middle function as x approaches 0 must also go to 0 by squeeze theorem. And so we have that we can say that the limit of x squared cosine of 20 pi x as x approaches 0 is equal to 0 as well. Okay, so that is that. Okay, so we're going to do another example, or more than one example actually. Page 8. So we want to find the limit, once again, if it exists, for this function. So we have the limit of 2x plus 12 divided by absolute value of x plus 6 as the limit of this function as x approaches negative 6. Okay, so as you can see right away, if you replace x with negative 6 using the direct substitution property, you're not going to get a result that you want. You're going to get, this expression is going to be undefined and the limit is not going to exist. But what did we say? We say let's simplify the expression as much as possible, and then if the limit does not exist, then it does not exist. It in fact may not exist, but we need to do what we are supposed to do, which is simplify this expression first. So using the definition of the absolute value, so recall, by the way, so the solution starts from right here. So recall the definition of the absolute value. We said that if you have f of x equals absolute value of x, then this is equal to x. If x is greater than or equal to 0, it's equal to minus x if x is less than 0, right? We saw this in probably Math 126, the definition of the absolute value. Right, so we're going to use that for this, for the denominator of this expression. So therefore, or thus, we can say the following. We can say that absolute value of x plus 6 is equal to x plus 6 if x plus 6 is greater than or equal to minus 6, right? Just this piece, minus 6. Let's see. No, sorry. Let me correct that. So greater than or equal to 0, not negative 6, but that. So x plus 6 is greater than or equal to 0, or minus x plus 6 if x plus 6 is less than 0, right? Okay. We know that. So let's simplify this. So from here, then, we can rewrite all of this by saying that, so this is x plus 6 if x, let's solve for x here, x greater than or equal to minus 6, and then minus x plus 6 if solve for x here, x is less than minus 6. Okay? So if the limit of this expression exists, then as we approach from left to right to negative 6, we must get the same value, right? So if we approach x, if the limit of this function as x approaches negative 6 exists, then as x approaches negative 6 from left and as x approaches from the right, we should get the same limit value. That's how we can say that the limit of this function exists as x approaches negative 6. So let's find that out. Because this denominator, the limit of the denominator would be using this function if we're approaching, x is approaching negative 6 from the right. Because if x is greater than or equal to negative 6, that means from the right, we need to use this function. If x is less than negative 6, that means if x is approaching negative 6 from the left, then this is our function. So let's find the limit of that function from the left and from the right as x approaches negative 6. Okay? So once again, therefore, the limit of the original function, which is 2x plus 12 divided by absolute value of let's see. So absolute value of x plus 6, as of course, let me make sure that this stands out, as we approach negative 6 from the right. From the right, that means we need to use x plus 6, right? So this is equal to limit of that function as we approach negative 6 from right. We need to replace this absolute value quantity with this version of it, this piece of it, for whenever x plus 6 is greater than or equal to 0. So 2x plus 12 divided by x plus 6, right, from the right, which is that. Okay, so this is now equal to, let's factor the numerator. What do we end up with? We end up with the limit of this function, 2x plus 6 divided by x plus 6 as x approaches negative 6 from the right. So these two terms cancel out. We end up with, so this is simply equal to 2, right? These cancel out. Limit of a constant as x approaches any value is equal to the constant. That's one of the properties we have. Okay, so this is the limit from the right. From the right. Okay, so let's take the limit from the left, which means we have to use this piece, because when x is less than negative 6, or that means when x approaches negative 6 from the left, then we need to use this piece for the denominator. So we have limit of 2x plus 12 divided by, and let me just make sure that it says it here, as x approaches negative 6 from the left, it would be equal, the denominator would now be equal to this, right? X approaching negative 6 from the left. So minus x plus 6. So this is equal to, then once again, let's factor the numerator just like before. Limit of, as we approach negative 6 from the left, so once again, we have these two cancel each other out. We end up 2 divided by negative 1, and limit of a constant as x approaches anything is equal to the constant. So we have negative 2. And this is limit from the left, right? That was limit from the right. This is limit from the left. On the left. Okay, so do the limits from the right and left agree? They don't. What does that mean? We learned in the last video that if the limits from the right and left do not agree, then the limit does not exist. So negative 2 is not equal to 2, therefore the limit of as limit of this function does not exist. As x approaches negative 6, does not exist. Okay. Okay. So let's see more examples here. Okay, so suppose, and this one, this is part A, and then we have a part B for this. So we want to find the limit for the following. So we have the limit of sine of 3x divided by x as x approaches 0. We want to know what is that limit equal to. Okay. All right, so let me remind you of an identity that we introduced earlier, and that's this identity, that the limit of sine of theta divided by theta as theta goes to 0 is equal to 1. Always this is true. Okay, so do we have that? Do we have sine of 3x divided by 3x? No, we don't, right? So what are we going to do? Well, we can multiply the numerator and the denominator by 3 over 3, right? We can get it. We can, right now, this expression is not there. So we couldn't apply this identity right away, but it's really easy to modify this expression such that we can apply this identity. We can simply multiply this by 3 over 3, which means multiplying this expression by 1, which doesn't change anything, right? We're allowed to do that. So let's do that. So we can say that 3 divided by 3 times what we have, right? Sine of 3x divided by x. Okay, so we have that. And so right then, after we do that, we can say this is equal to 3 times, now put this 3 underneath this expression. So 3 times sine of 3x divided by 3x. Okay. Now we have sine of some quantity divided by that same quantity. So let's now take the limit of this expression. So therefore, limit of all of that, which is 3 times sine of 3x divided by 3x as x approaches 0. Okay, so applying the properties that we've learned about, we know that the limit of a constant as x approaches anything is equal to the constant itself. But let's apply the properties anyway. That. And so all of this times limit of that, the second piece. Like that. So on the first term reduces to 3. The second one, we know that it reduces to 1 according to the identity we have. So that is equal to 3. So notice again, if you replace, substitute x with 0 right away, you're not going to get any limits. First, you need to simplify according to what we did, this procedure, and then substitute for x with 0. And of course, in this case, we did find the limit. Okay, so let's do another example similar to this, or part B of this. So we want to find the limit of sine of 4x divided by sine of 6x as x approaches 0. So we want to find this quantity. Okay. So solution, again, let's recall that very useful identity, right? So recall that limit of sine of theta divided by theta as theta approaches 0 is equal to 1. So we have that identity, right? So now we need to get these two to a point where we can apply this identity, because right away, if you substitute for x with 0 right away, you're going to get 0 over 0, which is undefined. So the limit does not exist. But we can't be sure until we simplify and then use this direct substitution method. Okay, so let's simplify. So the way we can do that is, first of all, for this piece, we need a 4x in the denominator, right? So we can multiply the numerator and the denominator by 4x over 4x. So 4x over 4x times that expression right, like that. And then we also need to do something about this sine of 6x, right? So let's multiply the same expression by 6x over 6x. right? That quantity, 6x over 6x, or the argument of the sine function in the denominator. Okay, so now by rearranging the terms, so rearranging terms, so by just moving things around, okay, what are we going to have? We're going to have from these three, 1, 2, 3 terms, what can we say? We can say that 4x, or that one, times sine of 4x divided by this one, divided by 4x, right? So we just put this underneath this. Then let's put these 6x and sine of 6x terms together. We can write 6x, that term, divided by this denominator, right? Times, what are we left with? 1 over 6x, right? 1 over 6x. Okay? Like that. Then we have, okay, so from here, 4x divided by 6x. Let's put these two together. So this one, put these together. Okay, put them together. Put these together. That one and that one. And what do we end up with? We end up with 4x divided by 6x, right? Putting those together. We end up with sine of 4x divided by 4x. So this and that have been put together. This is we keep this because this is useful. And how about this? Can we apply this identity to this right away? No, because this is reverse of that. This is the reciprocal of that, right? This is the reciprocal of that. So we can't apply the property right away, but we can write this expression, take the reciprocal of it such that we would get the same thing. In other words, 1 over sine of 6x over 6x gives us the same thing. This is equal to that. Okay? It's the same thing. So now we can take the limit of what we have because the arrangements are such that we can apply this useful identity. Let's do that. So now simplifying, this one simplifies because the x's cancel out. We end up with 2 over 3, right? From this first ratio, we get 2 over 3. Then this one, well, I should have simplified it there, but it's okay. Because we need to take the limit of the whole thing at once, and I should have simplified it there, but it's okay. It makes it clear that way where this 2/3 is coming from. So it's actually more useful, I think, that we have this step in between here. And then 1 over sine of 6x over 6x. Okay, now let's take the limit of everything. So we have the limit of 2/3 as x approaches, as theta approaches. So in this case, just let me clarify. So theta is just a variable, right? In our case, that's just x. So it's okay if we use x. And then limit of as x approaches 0, limit of sine of 4x divided by 4x as x approaches 0, and limit of 1 over sine of 6x divided by 6x as x approaches 0. Okay, again, this theta can be anything, any variable. In this case, it's just, in this case, it's 4x here, it's 6x here, and so on. Okay, so we know that the limit of a constant as x approaches anything is just equals to the constant, so 2 over 3. We know that according to the identity we have, sine of theta divided by theta as theta goes to 0 is equal to 1. So this whole thing is 1. Also, this would be 1 as you apply this limit to this denominator of this complex fraction, you get 1, right? You get 1 over 1 as you apply this to that. So once again, you get 1. Therefore, the final answer is 2/3. So that's the limit. 2/3 is the limit of this expression as x approaches 0. Okay. So these are useful examples to get us kind of get back into the trigonometric mode. Okay, so let's do more examples here. Suppose if we have the limit of this expression, tangent of 6t divided by sine of 2t as t approaches 0 is equal to what? That's the question, right, that we want to answer. Okay, so from trigonometry, we know that tangent of 6t is equal to sine of 6t divided by cosine of 6t, right? So let's make use of that relationship. So this whole thing, I'm just going to deal with this expression, and then I'm going to apply the limit to the simplified version of that expression. So then we have sine of 6t divided by cosine of 6t divided by sine of 2t. Okay. Then, in order to apply the identity that we have, that sine of theta divided by theta as theta goes to 0 is equal to 1, the limit of that, limit of sine of theta divided by theta as theta goes to 0 is 1. In order to apply that, we need to have a 6t somewhere, right? So, but before that, let's simplify this complex fraction. So let me do that here just to save a little bit of space. So we have sine of 6t divided by sine of 2t times cosine of 6t. Okay, so let us multiply the numerator and the denominator of this expression by 6t. Okay, we need that. We need that 6t. Okay, so 6t over 6t multiply by that expression, sine of 6t divided by sine of 2t times cosine of 6t. Okay, so now we can write 6t, and we need the 2t as well, right? We need this argument as well. So let's multiply. So what we do is let's multiply this whole expression by 2t over 2t. So we have, once again, I'm going to keep these in blue because that's what we're introducing into this expression, times sine of, so times, well, times sine of 60 divided by sine of 2t times cosine of 60 times 2t divided by 2t. Okay, we need that argument as well because it's there. Okay, so now let's simplify things a little bit. So we have, let's put this 6t and this 2t together. So we have 6t divided by 2t times sine of 6t divided by this 6t. Sine of 6t divided by this 6t. So we're just rearranging things, that's all. Multiplying the original expression by 60 over 60 and 2t over 2t doesn't change anything because we're multiplying by 1, but it helps us tremendously because we're going to, pretty soon, we're going to be in a position to apply that identity that applies to the limit of a sine function divided by the argument of the sine function, right? Okay, so that. And then this 2t, we already have that as part of the denominator here, but we're left with this 2t. This 2t over sine of 2t, right? So 2t divided by sine of 2t. What are we left with? We've rearranged everything except one last term, right? This cosine 6t doesn't appear anywhere here, so 1 over cosine of 6t. So we brought out the cosine, 1 over cosine of 6t from this expression. Now it's by itself here. Okay, and as you'll see in a minute, this is a very useful arrangement. Okay, so let's simplify. What do we have from the first expression? We have simply 3, right? So this is 3. And then we have the, and the rest of this is the same thing. So let me, sine of 60, and I'll apply the limit in the next step. But I didn't want to apply the limit before I simplified the t from here, okay? Because that would give us 0 over 0, which would be undefined. So it's a good thing that t canceled out from this first term. Okay, like that. Now let's take the limit of the whole thing. So from the first expression, we have the limit of 3 as t goes to 0 times the limit of sine of 60 divided by 60 as t goes to 0 times, we need to take the reciprocal of this, don't we? Just like the previous example. So the limit of, let me do that at the same time, 1 over sine of 2t over 2t. 1 over sine of 2t over 2t is the same thing, right? As t goes to 0 times the limit of t, or limit of this function, 1 over cosine of 6t as t goes to 0. Okay, so let's see what do we have. Applying the properties we've learned so far, this would be simply 3, right? 3. What about this one? Limit of sine of 60 divided by 60 as t goes to 0, 1. Limit of that as t goes to 0 is equal to 1, right? 1. Limit of cosine of 0 is, do you remember from the trigonometry what it was? Cosine of 0 is equal to 1. cosine of pi is equal to -1, right? So this whole thing, we don't need any identity for this one. This is just 1. So 1 again. So we end up with 3. Okay. So could you have gotten this result if you didn't simplify this expression, if you just plugged in? No. So simplifying that expression and putting it, arranging the terms such that we can apply the identities and properties we've learned is invaluable. And I keep highlighting that in these examples because that's key in being able to solve problems in this class, in the next calculus class, and the one after that. Okay, so please remember these techniques. So let's do another example. So we have cosine of theta -1 divided by, we want to find the limit of this expression, sine of theta equals what value? Okay, once again, you can see that if you immediately substitute for theta with 0, the whole thing becomes undefined. So let's see if we can simplify this in any way. So let's begin by multiplying both the numerator and the denominator by cosine of theta plus 1. And in a second, you'll see why. But let's start from there. So multiplying, so this is where the solution begins. So this is solution, multiply by cosine of theta plus 1. In particular, we're doing this because it's going to help us a relationship we learned about in the trig class, Math 127. Okay, so we're going to do that. Again, let's simplify and then we're going to apply the limit after we've simplified this expression. But cosine of theta plus 1 divided by cosine of theta plus 1 multiplied by that expression, cosine of theta minus 1 divided by sine of theta, right? We're simply multiplying the expression we have by 1, because what is this divided by that? It's just 1, all right? Okay, now multiply these by each other. What do we get? We get, well, I don't want to skip any steps. It's better to show all of it. So cosine theta minus 1. And then, of course, we have sine of theta times cosine of theta plus 1. Now, the numerator, we get using this expression from pre-calculus, using x plus y times x minus y equals x squared minus y squared. Using that, we can write cosine squared theta minus 1, right, for the numerator, and that is divided by sine of theta times cosine of theta plus 1. Okay, so now recall that sine squared theta, this is from trig class, right, plus cosine squared theta is equal to 1. Therefore, let's find the equivalent of this. And thus cosine squared theta minus 1 is equal to, if you rearrange things, you will find out that that expression, which is equivalent or identical to this, is equal to minus sine squared theta. Okay? So this is why we multiplied the numerator and the denominator by cosine theta plus 1 over cosine theta plus 1. Okay? So that expression is equal to that. So let's substitute for it. We have minus sine squared theta divided by sine theta times cosine theta plus 1. Right? So we can cancel one of the sine theta with this, so we end up with minus sine of theta divided by cosine of theta plus 1. Okay, so this is as far as we can simplify this expression. Right? This sine of theta canceled with one sine of theta from here. We end up with 1 minus sine of theta only over that piece. Okay, now let's take the limit. So we have the limit of minus sine theta divided by cosine theta plus 1 as theta goes to 0, right? Yes, as theta goes to 0 would be equal to, simply substitute for theta with 0. And if we end up finding out that the limit doesn't exist, so it doesn't exist, no big deal. That happens too. But let's see. So this will be equal to minus 0, right? Sine of 0 is just 0, divided by cosine of 0 would be 1, or cosine of 0 would be 1. Cosine of angle 0 is 1. Cosine of pi is negative 1. So this would be 1 plus 1. So we end up with 0 over 2, which is 0. Okay, like that. So the limit does exist. The limit of this expression as theta approaches 0 does exist, and it's equal to 0. Okay, so we have come to the conclusion of this section. Please practice with more problems and let me know if you have any questions. And I thank you for persisting through this video as usual. For now, have a nice day, and I'll see you all again next time.